A key component to understanding the Earth is geologic mapping. The real challenge of mapping is taking three-dimensional rock outcroppings and translating them to a 2D map surface. Learning how to make a geologic map is a key component in an undergraduate geology degree. Most students have a 6-week field camp, 1 or 2 summers, to hone their mapping skills before graduation. One of the areas where students from all over the country come to learn mapping just happens to be here in southwest Montana. It's called Block Mountain. It has great rock exposures and folded rocks and lava flows to provide an approachable but legit proving ground for the budding geologists. So let's explore it. Look into what it takes to make a geologic map at Block Mountain. So as a geologist, what we're doing out here when we're trying to make a map is we're trying to take this natural three-dimensional area and represent it on a 2D piece of paper. So first what we're looking for is what's called an outcrop. An outcrop is rocks cropping out, if you can imagine that, from the earth. So we know they're attached to the earth. So you see this little hog back here, it extends down beneath the soils, and so we know it's representing what the crust of the earth was doing, at least to some depth. Then what we do is we come in, make sure we have some sort of safety glasses on, and we smack off a piece of rock to get an identification. And the reason we're breaking it off is so that we're getting away from just what's on the surface, which may be weathering that doesn't tell you what type of rock that is, and we're trying to identify that rock. So we commonly use a little loop or a hand lens to get a microscopic look at that rock as well, or at least a zoomed in look. And then what we do, and this is really how we take the 3D and put it in a 2D representation, is this is a limestone. So I've taken a look at this rock and it's a limestone. So this limestone would have been laid down flat. Clearly, as we look at this unit and this ridge, what we can see is bedding going this way. So that bedding should have been flat. Now it's been somehow turned up, and that's through tectonic processes. So we're trying to map that. So the first thing we do is we take what's called a strike. So we're taking what's called a strike and dip, and that's the convention of mapping. Here we're measuring this direction. So I use my compass and take note of that direction. It's, as you can see here, the north arrow is pointing, it's nearly a north-south strike. And then the dip is perpendicular to that. Easier to think about, the dip is perpendicular to the strike. So we use the right-hand rule. If I go down dip, the strike is in the direction of my thumb. And then what we do with this compass is we measure the angle from the horizontal down. So here it's going to be about 80 degrees. And so that's the convention of mapping. And then on a map, we have a specific symbol for that strike and dip. And if you look around here, even this ridge itself, the strike and dip changes as it goes down. So this ridge is curving, so the whole thing has been uplifted, tilted, but also folded. And so we have different specific notations on the map, the 2D sheet of paper, to represent the 3D orientations of these units. And so what you do as a good field geologist, you take as many strike and dips, as many field locations as you can throughout the day. So this unit here appears to be a limestone ridge. If we look off to the right, off to the east, it appears there's another ridge with probably a different composition. So you would do the same thing over there, and then you would continue, depending how much time you have and how big of an area you're mapping, to do that for a day, a week, a month, several months to map this area. So recently, Dr. Stuart Parker from the Montana Bureau of Mines and Geology has made a professional map of this area, and it turns out to be just a beautiful place. Students have been mapping in this area for dozens of years, and so they've contributed to that based on their unpublished yet beautiful maps. So this is what you do as a field geologist coming out to map in an area like this, which is mostly composed of sedimentary rocks that have been tilted on their end. We've come a bit farther into the Block Mountain mapping area, actually to the north, and we found a similar, if not that same, limestone unit. And here, if we look at it again, we can see that instead of these layers being flat, they've been tilted up. And so again, they're dipping to the west, which will be to our left. And so something has deformed these units. However, as you look here, just a little bit to the right of this main unit, you start to see they're actually curving. So this unit has undergone significant deformation through tectonic activity. Wow, look at this. If you look up at this unit again, you can see it's almost like a wave that would be breaking over our head. And as you get closer in here, you can see that wave. However, if you look up above, you can see that that is actually then folding back to the east. So we have it dipping here to the west, and then dipping to the east, and then back to the west, and then back to the east. And so we have a full fold here that you can map. And so what you would do to map that is you make sure you're on the bedding plane, and then you take the hinge of that fold, the tight curve of that fold, and you map the trend, the direction that that fold is trending. And there's a special symbol for that on the map. So just an amazing example of a fold here running through these rocks. These rocks were deformed at some point, and your job as a mapper is to make these observations, translate them onto the map, and see how it compares to the rest of it, and then make your interpretation. Certainly important to make your observations first, because as we come over here, you can see, again, another fold in this rock. So this outcrop is folded like a little dome, and so right then you would argue that the compression direction was from the right and left, or the east and west, compressing that together to fold it up. However, you have to be careful to not overinterpret when you're in the field. Make your observations, put them on paper, represent this three-dimensional surface in 2 dimensions, and then make your interpretations. So what a great place to learn out here at the Block Mountain mapping area. Just phenomenal look into Montana's geologic history. In the quest to map the geology and take it from the real world onto a sheet of paper, there's one final challenge down here by the Big Hole River in the southeast portion of the Block Mountain map area. And so this is a rock unit that looks fundamentally different than the others. It has this systematic pattern of cracks that going through it. And those cracks appear to manifest in a form of shapes. So if we look up into this, we can see that there's roughly hexagonal shapes there. Let's look closer at this unit to try to figure out its genesis. So as we look at it closer up, if you look on this weathered surface here, you can see all of these very small little holes right there. And then also if we look at the composition of the unit, look in here, we can see that it has a very dark ground mass with these minerals, these greenish minerals in that ground mass. So what we're actually looking at here is a volcanic rock, a lava flow on the surface. It's called a basalt, an olivine basalt. That mineral, green mineral, is olivine. And these fractures are actually cooling joints. So as this unit came to cool on the surface, it cooled slowly, and these cracks propagated from the top and the bottom. Also, what we see throughout it are these little inclusions. So you have sedimentary rock that's included into this lava flow as it came up to the surface. It plucked off what it was coming through, and those are called xenoliths. So this is a lava flow that would have erupted. It's younger than all the units around it because it's on top of them. So it would have erupted on the surface and flowed in the low areas, just like water would flow in the drainages. It came to rest, and then it jointed. So this is actually the Block Mountain lava flow. It's a 47 million year old columnar jointed basalt. So just a beautiful way to end the mapping experience here at Block Mountain with this type of rock that's going to behave fundamentally differently than the sediments below it. And so that's yet another thing to figure out as you put this on the map. And a beautiful spot to do it, that's for sure. Montana Geology doesn't disappoint. Well, this is pretty fun because Dr. Stuart Parker and others here at the Montana Bureau of Mines and Geology published a map of Block Mountain in 2025. So how do all those things we saw in the field represent on a 2D map? Well, what we can see are different colors for different rock units, and you can see them striking in more or less that north-south direction. Also, those sedimentary rocks are folded in different areas. And then you can see here in red all these little different symbols showing different anticlines and other aspects of folding. And these little black symbols represent the strike and the dip of those units. So that's how we're taking those three-dimensional real-life rocks and putting them on a map so that we can understand how they're behaving. Then you have all those sedimentary rocks. You can see this purplish is the Block Mountain lava flow, and it just sort of flows across and wherever it wants based on the drainage 47 million years ago. So that's what the Block Mountain area looks like on a professionally done geologic map here at the Montana Bureau of Mines and Geology.